In the last lecture, we were looking at the use of correlations in balance equations. Okay. First, we had discussed the limit of low Peclet number, where the transport was due to diffusion, and in that case the Nusselt number is equal to 2, or the Sherwood number is equal to 2. Note that at low Peclet number the velocity makes no difference, and therefore the Nusselt number cannot depend on either the Peclet number or the Reynolds number. Okay. And therefore, the Nusselt number or the Sherwood number has to be a constant. That correlation, Nusselt number is equal to 2, was derived under the approximation of steady state. That is that the time taken, that is that there is no variation in the temperature. Okay. Difference between, for example, the particle and the ambient fluid. There is no time variation, or there is no time variation in the temperature between the fluid and the pipe wall in the case of flow through a pipe, and so on. If we are to use it for unsteady problems, for example, a sphere cooling in a fluid, the sphere will take the temperature of the sphere will decrease as time progresses. Okay. The temperature of the sphere will decrease as time progresses, and therefore one has to use correlations, okay, which are derived at steady state for this particular case. It can be used only if the diffusion time, length square divided by diffusivity, where the length is the characteristic length. If that time is much smaller than the time taken, the characteristic time, that is the time taken for the temperature at the sphere surface to vary, in that case you can instantaneously assume that the system is at steady state and then go ahead and use a correlation. The characteristic length in the case of diffusion problems is just the dimension of the particle itself. In the case of flow of diffusion from particles, it is the tube diameter in the case of heat transfer across a pipe wall and so on. So, the diffusion time can straightaway be calculated from that. In forced convection problems, it turns out that the length scale for diffusion is much smaller than the dimension of the pipe or the particle. Okay. And the reason for that is as follows. Okay. You have flow around a particle. Okay. You have flow around a particle. And the temperature of the particle, for example, T naught, is higher than the ambient temperature. Okay. And because of that, energy diffusing from the surface of the particle will get convected downstream, okay, due to the flow. Therefore, it will not be able to diffuse very far before it gets convected downstream. And as the strength of convection, the free stream velocity increases, or the Peclet number increases, this disturbance to the temperature field due to conduction from the wall will be restricted to a thinner and thinner distance close to the surface. And therefore, the characteristic diffusion length in this case is not the sphere diameter, but rather the thickness of this region, okay, over which diffusion is taking place. Okay, it is called the boundary layer thickness. The thickness of this region over which diffusion is taking place is the characteristic diffusion length in this case. And this characteristic diffusion length is much smaller than the diameter of the sphere. So, obviously, the time it takes to establish a steady state over this length is also going to be much smaller than the time taken to establish a steady state over the diameter of the sphere. Okay. In the case of flow around particles with a rigid surface, this length goes as p e power minus 1/3. Okay. Mobile interfaces, it goes as p e power minus half for a bubble, say. Okay. For films and for flow in a pipe or in a film, the exponent is once again 1/3, okay, except that it is equal to p power minus 1/3, okay, times d by L power minus 1/3. Okay. It is equal to p power 1/3 times d by L power minus 1/3, and for the transport into a liquid film, okay, a gas liquid transport, this is P power minus half times h by L power minus half. Okay. Note that this is going to be much smaller. So, this the diffusion length by the characteristic length is this. This has to be smaller than 1, okay, if it is convection dominated. And in the case of the rigid pipe flow and the falling film, this is much smaller than 1 only if L by H is much smaller than P E, or for a pipe flow D by is much smaller than P. Okay. So, it is valid only in this case. Okay. And the diffusion time goes as L d square by alpha. That means that the diffusion time divided by this diffusion time this for in the absence of flow, that goes as P power minus 2/3 or P power minus 1 for P power minus 2/3 for rigid surfaces, and it will go as for mobile. Okay. And we were using this to try to solve a problem. Okay. A steel sphere of diameter 1 centimeter with initial temperature 300 degrees centigrade is cooled in a stream of cold air at 0 degrees. Free stream velocity is 1 meter per second. Time taken for temperature to decrease to 100 degrees centigrade. Okay. So, unsteady state problem, as the sphere is losing heat, it cools down, and you want to find out what is the time taken for the temperature to decrease to 100 degrees centigrade. Examine the steady state assumption, and the properties were given, and this problem we are solving assuming a laminar flow. Okay. Okay, assuming that the flow is laminar, that is, we are not going to take into account the effect of the boundary layer separation and wake and so on in this particular estimate. Okay. We had calculated the thermal diffusivity of air K by rho Cp 1.92 into 10 power minus 5 meter square per second. Peckley number was large. Okay. So, we decided that we will use this correlation for high Peckley number. Okay. How do we calculate the temperature decrease? Okay. The rate of change of energy of the sphere, okay, rho of the sphere, the specific heat of the sphere times the temperature by dT, okay, is equal to minus pi d square times QAV. Okay. Pi d square is the surface area, and Q average is the average heat flux from the surface. Okay. This I should actually multiply by the volume. Okay, so into pi d cubed by 6. Pi d cubed by 6 is the volume of the sphere. Okay. So, this mCp into the rate of change of temperature is the rate of change of energy, okay, the rate of change of heat energy. That heat energy changes because there is a conduction of heat from the surface and convection in the presence of the mean flow, okay, and that is taken into account by the second term here, pi d square times the average heat flux. Okay. So, therefore, the rate of change of temperature is equal to minus 6 by rho s Cps into d, okay, into Q average, and then I substitute the Nusselt number correlation. Okay. Okay. The Nusselt number correlation, as I said, was that is Q average by K, okay, Ts minus Tf, by d is equal to 0.992 P e power minus 1/3. Okay. Where T initial temperature of the sphere is this, the instantaneous temperature, of sphere is equal to Ts, and the temperature of air is, I have written it as Tf. Okay. Temperature of air is written as Tf. Okay. Yeah. So, the instantaneous temperature of the sphere is Ts, Ti is the initial temperature of the sphere, and temperature of air is Tf. Okay. So, this is where the approximation is made. In this relation, I have substituted the instantaneous temperature for the sphere for the sphere temperature in the correlation. The correlation is valid strictly only for steady state, but here I have substituted the instantaneous temperature of the sphere. Okay. So, this can be substituted for Q average, okay, and I will get 6 by rho s Cps d, okay, into K Ts minus Tf by d into 0.992 P e power minus 1/3. Okay. So, that is the rate of change of the temperature of the sphere. Okay. Note that on the right side I have Ts minus Tf, and Tf is a constant. Okay. So, I can include all of the other factors in a time constant by the characteristic time. Okay. Where Tc is equal to rho s Cps d square kindly note a mistake here, this should be P e power plus 1/3, not P e power minus 1/3. Okay. Nusselt number is P e power plus 1/3. The boundary layer thickness is P e power minus 1/3 times d. Okay. So, kindly note that difference. In the limit of high Peclet number, the Nusselt number has to be large compared to 1. So, it is P e power plus 1/3. Okay. So, this is rho s Cps d square by 6 Ka into 0.992 into P e power 1/3. Okay. And I can evaluate this, okay, using the properties that I had for the thermal conductivity etc. for the sphere and for air, and the Peclet number that I had subsequently calculated. Okay. So, I can use all of those. Okay. This was 8 into 10 power 3 density kg per meter cubed, okay, and the specific heat was 500 joules per kg per degree centigrade, and the diameter of the sphere was 1 centimeter or 0.01 meter. Okay. Divided by 6 into thermal conductivity of air was 2.4 into 10 power minus 2 watts per meter per degree centigrade, okay, into 0.992 into Peclet number per 1/3, that is 520.8 whole power 1/3. Okay. And you can work out this calculation, and the final result comes out to be 348 seconds. Okay. So, this is the characteristic time for the cooling of the sphere due to forced convection. Okay. Now, this equation here, okay, dTs by dt, okay, can be solved, okay, to obtain T final temperature minus Tf divided by T initial temperature of the sphere minus Tf, okay, is equal to e power minus T by Tc. Okay. Note that dt by dt is equal to minus Ts minus Tf by Tc. Okay. Integrate that once, dt by dts is equal to minus dt by Tc. Okay. Log of Ts minus Tf is equal to e power plus some constant, which means that Ts minus Tf is equal to minus a e power minus T by Tc. Okay. And then at T is equal to 0, Ts is the initial temperature, okay, which means that Ts minus Tf is equal to Tsi minus Tf e power minus T by Tc. Okay. So, Ts minus Tf is the initial Ts, the initial temperature difference. The temperature difference between the sphere and fluid at time t is equal to the temperature difference at initial time t is equal to 0 times e power minus T by Tc. Okay. So, that is the expression for the temperature in sphere. Okay. Now, we have to calculate the time taken. Okay. We have to calculate the time taken for the sphere temperature to go from 300 degrees centigrade to 100 degrees centigrade when the fluid temperature is 0 degrees centigrade. Okay. So, therefore, T fluid is equal to 0 degrees centigrade, T initial temperature is equal to 300 degrees centigrade, okay. The final temperature is equal to 100 degrees centigrade, okay, which implies that Ts minus Tf is 100 degrees centigrade divided by the initial temperature minus the fluid temperature is 300 degrees centigrade is equal to e power minus T by Tc. Okay. And you can solve this to get T is equal to 1.1 Tc, okay, which is approximately equal to 382 seconds. Okay. Okay. It is approximately about 6.4 minutes. Okay. That is the time it takes under the current of air for the temperature to decrease from 300 degrees centigrade to 100 degrees centigrade. Okay. And finally, I have assumed in the correlation that the Nusselt number, Peclet number correlation is derived for a steady flow. So, I have to verify at the end that the flow is actually that the time required for reaching steady state is much smaller than this time taken for the change in temperature of the sphere. Okay. I have to verify that the time taken for steady state is much smaller than the time taken for the change in temperature of the surface of the sphere, which is 382 seconds. Okay. Time for steady state, or rather the diffusion time, okay, for the system to reach steady state is equal to P power minus 1/3 times the diameter d. Okay. I am sorry, P power minus 2/3. Okay. So, let me first go back. Okay. Diffusion length is equal to p e power minus 1/3 times d. Okay. That means that the diffusion time is equal to the diffusion length square by alpha. This is alpha of the air. Okay. This is going to be equal to 520.83 power minus 1 by 3 into the diameter of the sphere is 0.01 meter, the whole thing square divided by, we had calculated 1. Okay. And if you calculated this comes out to be 0.081 seconds. Okay. And you can easily see that this is much smaller than 382 seconds. Okay. So, it reaches steady state very fast, and that is the reason that I can use a correlation that is valid at steady state in this case. Okay. Because the characteristic time is of the order of more than 300 seconds, whereas the diffusion time it takes for establishing the temperature field around the particle is only less than 0.1 seconds. Okay. So, this is an example where the temperature of the boundary is changing. Let us consider an example where the boundary condition or the diameter itself is changing for a particle, that is the boundary surface itself is changing. Okay. A pill of diameter d naught, or say initial, and rho p is made of soluble that if the pill is moving with velocity v c, what is the time for the pill to dissolve? Assume Reynolds number is small, the concentration at the surface is Cs. Okay, so that is the problem. Pill of initial diameter d naught was dissolving. Okay, the density of the pill is rho p. Surface concentration in the liquid is Cs. Diffusion coefficient is d. Okay. Rate of change of mass is equal to minus pi d square surface area into the average flux. Rate of change of mass is, I will use partial once again to not confuse with the diameter, of pi by 6 rho d cubed. Okay. It should be rho p because that is what I have used for the pill. It is equal to minus pi d square J average. Okay. Taking the derivative, I will get rho p pi by 2 d square partial d by partial t is equal to minus pi d cubed J average. Pi and d square cancel. My apologies here, this should be a square surface area, that is d square. Okay. Okay. Partial d by partial t is equal to 2 JAV by rho p. Okay. Now I use the Sherwood number definition. Sherwood number is equal to J average by d CS by the diameter, okay, to substitute for J average. Okay. So, this is equal to 2 d CS times the Sherwood number divided by rho p d. Okay. And then the Sherwood number correlation, which is the same as the Nusselt number correlation in terms of the Peckley number. High Peckley number, low Reynolds number, 0.992 times the Peckley number per 1/3. Okay. Into 0.992 into the velocity of the sphere, okay, Vc times d by diffusion coefficient per 1/3. My apologies, there should be a negative sign everywhere here. Okay. This negative sign has to carry through. Okay. Okay. So, there should be a negative sign here, negative and negative. So, this is equal to minus 1.984 into Vc per 1/3. This is the characteristic velocity, so it should be Vc okay. The diffusivity per 2/3 into Cs divided by rho into d per 2/3. Okay. This is partial d by partial t. Okay. And I can take this factor of d power 2/3 to the left side, d power 2/3 to the left side. Okay. This is rho p. And I can integrate it once, okay. 3 by 5 d power 5 by 3, okay. D power 2 by 3 integral is d power 5 by 3 into 3 by 5 is equal to minus 1.984 Vc per 1/3 d power 2/3 Cs by rho p into t plus some constant of integration A. This constant of integration is determined from the initial condition. That d is equal to d naught at t equals 0. And if I just substitute that, I will get 3 by 5 into d naught power 5 by 3 minus d power 5 by 3 is equal to 1.984 Vc per 1/3 d per 2/3 Cs t. T by rho p. I have taken this constant, this time to the left side, and the diameter has been taken to the right side. Okay. I could also write this in terms of d minus d naught, in which case I will get d per 5 by 3 minus d naught per 5 by 3, and this will have a negative sign in it. Okay. You can express it either way. Okay. Either d minus d naught, which will be negative because d is smaller than d naught as the sphere dissolves, or the other way around, d naught power 5 by 3 minus d power 5 by 3. Okay. What is the total time for dissolution? Okay. Td is equal to time at which d is equal to 0. Okay. The diameter has to decrease to 0. Okay. That is the total dissolution time. Okay. And therefore, I can calculate the total dissolution time as the time at which d is equal to 0, which means this is equal to 1 by 1.984 into 3 by 5, comes to about 0.3 rho p d naught per 5 by 3 by Cs Vc per 1/3 into the diffusion coefficient per 2/3. Okay. So, this is the time it takes for the sphere to dissolve. Okay. Is this time much smaller or much larger than the diffusion time? Okay. So, for this to be valid, you require that this dissolution time, okay, T dissolution has to be much greater than the diffusion time required for diffusion. Okay. In this case, the time required for diffusion, okay, is the length for diffusion, that is the characteristic length times p power minus 1/3, okay, the whole square divided by the diffusion coefficient, okay, which will be equal to the diameter of the sphere times p power d square p power minus 2/3 by the diffusion time. Okay. So, now you have to compare this time with this diffusion time, okay, and this I will leave it to you to do as an exercise. So, I have shown you a couple of examples for unsteady state transport, first heat transfer and then mass transfer from a particle, okay, due to forced convection at high Peclet number. Okay. The requirement is that the time required for diffusion should be much smaller than the time it takes for the variation of the temperature at the surface of the particle. This is for forced convection, and next lecture I will consider the case of natural convection. Under what conditions can we use steady state equations to model the heat transfer from natural convection to the density due to the density variations due to temperature variations. I will continue this in the next lecture. I will see you then.